Okay, welcome back, everyone. So we are privileged to have Dr. Josef Spillner and Panagiotis Gkikopoulos give us a tutorial session next. And their topic for today is acquisition and exploitation of insights into cloud applications. Dr. Spillner is a senior lecturer at the Zurich University of Applied Sciences. He is the team lead for distributed application computing paradigms and service prototyping. Dr. Spillner is a fellowship holder of the digitization initiative of the Canton of Zurich, and his teaching schedule is focused on big data computing, cloud native computing, and serverless computing. And with Dr. Spillner, we have Panagiotis Gkikopoulos. He's a PhD candidate and research assistant, also at the Zurich University of Applied Sciences. He received his master's degree in electrical and computer engineering from the University of Patras, Greece, specializing in information technology. And his doctoral work focuses on federated monitoring and data management and their application in obtaining trustworthy quality metrics for cloud software. So over to you, Dr. Spillner and Panagiotis.
Thank you very much, Sri Krishna, for the introduction. Welcome, everybody. Good afternoon, good evening. Namaste. We would like to present our work. I will start sharing my screen. You can see it?
Yes.
All right. So we are both working at the University of Applied Sciences. Applied means we work a lot, practically exclusively with industry. All the research we do needs to have a direct benefit to industry. We therefore often consider software as the primary output of our research activities. We also write a couple of papers occasionally, but we are mostly concerned with practical outputs that can be transferred directly to industry. And so we are looking at the trends and looking at what is important. And we would like to share in this tutorial with you some work we have done over the past 2 years, which is analyzing software artifacts used to build cloud applications in order to increase the quality of those applications. The tutorial will be split roughly into 2 parts. So I'm going to run you through a couple of slides, introduction slides in the beginning. And then my colleague will give you a more hands-on part, so where you can actually see how to run certain commands, how to install certain tools. And we also provide you, I will share the link later, with some companion material, because in the 90 minutes it may not be feasible to digest everything directly. So then I will share the links with you. You can follow on with additional material. So all of you have been through this conference now for 4 days. So I don't think I have to explain to you what is cloud computing, what are cloud applications. But it's interesting to understand that this has been a very strong trend now for about 10 years. And in fact, I remember the IEEE Cloud Conference when it happened 2009 in Bengaluru. I would have liked to visit the same place again, but now we are doing this online, which is, giving the circumstances, also fine. So cloud applications have exploded in various ways. So nowadays, you would not start software engineering anymore without any notion of service orientation and cloud integration, because we get all the benefits. We get the benefits of on-demand provisioning of our applications. When somebody wants to use the application, then at the click of a button, it is available. It scales elastically. If the application becomes very popular, then we can easily provide thousands or millions of instances. We only pay for what we use. And as a developer, especially the developer perspective is something we are considering with our tutorial. We have a rich service ecosystem available, lots of APIs we can use, programmable infrastructure, programmable platforms, but also a lot of hubs and marketplaces where we can find existing software artifacts, so we can easily plug together our applications. We don't have to write everything from scratch. So just like in the previous decades, we have used libraries, shared libraries. Nowadays, we want to build our applications on top of artifacts. And so our tutorial mostly aims at exactly this direction. We want to look at the artifacts we produce, but also the artifacts we take from other sources, and we want to understand them better in order to derive information and infer some information on how the applications will eventually work. Will they work at all? Will they have security issues? Will they crash? Will they work very well? That is something we can, to a certain degree, understand before we deploy the application by just analyzing these software artifacts. So if you have a look at those marketplaces out there, sometimes called hubs, we find that there are, of course, still the traditional artifact marketplaces where we find Python packages or Java packages or NPM packages for all the programming languages. But increasingly, we see cloud-specific hubs and marketplaces. So the screenshots you see here, they show you, for example, the Artifact tab, where we find an increasing number of packages that can directly be installed into private clouds based on Kubernetes. You see that the numbers, if you compare them, they are still modest. So if you look at the traditional artifacts, we typically are in the millions on MVN Central, on PyPy, and so on, whereas we are only in the thousands, maybe even just in the hundreds if you look at cloud artifacts. But it's clear that this number is now rising very steeply. We also see the AWS Serverless Application Repository, where we have another technology. In this case, it's more vendor-specific. Those applications can only be deployed to AWS. They are not directly portable to other cloud platforms. But again, such repositories, they are on the rise. So we have a number of cross-platform repositories, and we have a number of vendor-specific repositories. And if we build our cloud applications, we can, of course, depending on the platform we are using, choose the artifacts as we see fit. So here we see more advanced marketplaces. That includes, for example, decentralized applications, blockchains that started off in a completely different directions. But nowadays, we also find most blockchain offerings integrated into cloud. So if a part of our application should be decentralized and should be based on transactions that we can verify, then we can also find such marketplaces for dApps, for decentralized applications. And the screenshot you see below, it is taken from GitHub. We also see that a lot of such software artifacts are simply tagged accordingly on GitHub, and you can simply do a search. So in this case, if you build applications that need specific information for the deployment for GitOps, again, we find a whole class, a whole category of software artifacts. In this case, the artifacts for Project Syn, which is one of the GitOps platforms out there. So we have no shortage of those marketplaces, and the main issue for a developer is navigating them from a functional point of view, understanding which components, which services, which application parts that are hosted there are applicable to their own application, or where their own application should be published. But also from a non-functional point of view, basically all of those artifacts are free. There are some paid stores as well, but even if all of them are free, doesn't mean they are all working in the same way. So there are still other factors that we use to differentiate those offerings. So the price is one of them, but we also want to differentiate them on quality. We are both coming from Switzerland, so here the quality perspective is a lot more important than the price perspective. Companies are willing to pay for such software artifacts, but they need to be sure that certain characteristics are guaranteed, and that can be performance characteristics, security characteristics, of course, the functional correctness, the stability or fault tolerance. There may be several of those characteristics. So if you look at that from a software lifecycle point of view, and I'm just taking the lifecycle model that a colleague, Vasilis Andrikopoulos, has published 3 years ago, we see that typically we start with the artifacts that make up our application. So a couple of software artifacts, containers, cloud functions, and so forth. We deploy them. Then once they are running, they are delivering a number of services to us, which may be coupled to each other in a workflow or in different topologies. And we also have a number of choices how we deploy that. Should we, for example, if we need a database functionality, should we use the database functionality from the vendor, or should we host our own database components, depending on whether or not we have suitable artifacts available that we could boot up in a short amount of time, that we can replicate as much as necessary, and so forth. So in this whole life cycle, we see potential issues like, can we estimate the cost beforehand? Can we ensure that if we take in third-party components, the technical debt does not increase too much? Can we assure the maintenance over long term? Do we not introduce a number of security vulnerabilities? Are we protected from unannounced downtimes and so forth? And our hypothesis about 2 years ago was that not all of those issues, but a certain number of them we can certainly reduce or even eliminate if we perform a static analysis and then later combined a dynamic runtime analysis on these artifacts. And that can happen before the deployment. So here I share with you a model that I also present in our lectures when we have a lecture on cloud application development, and this is something that we introduced early on to give you a model of what we consider a typical cloud application. Of course, there are various ways to build software for the cloud, but that's an easy, intuitive model. It's that people start as an engineer creating their artifacts, and they may be container images, like, for example, Docker images. They may be functions like AWS Lambda. They may be smart contracts like we have seen in the dApps. There may be some larger virtual machine images, or we may have language-specific packages like in the past deployment, or even newer technologies like unicorns. All of those are developed, engineered, built, tested by the engineer in their working environment. They may also have some internal structures, which for our talk are not that relevant at the moment. So there could be workflow structures between them or compositions. And in the end, they get deployed. And as we see, a number of those technologies end up running as a container anyway, but that does not necessarily mean that the developer sees those containers. So when you deploy a cloud function, for example, you are mostly concerned with the source code that you edit in text mode, and then the cloud provider will, under the hood, turn that into a container that runs. But a lot of the characteristics of the running container can be understood if you have a model of the provider, plus if you have insights into those artifacts. So those artifacts here on top, those are the ones that we want to consider with our analysis. And of course, we are talking about cloud software and cloud applications, but just as an aside, it is clear that if we look forward, we see more complex infrastructures and topologies emerging, such as continuums that include edge processing, fog processing, direct processing, and IoT devices. And even there, it's more important to understand what are the characteristics of our software artifacts. For instance, if we want to have a dynamic migration of software artifacts, we need to understand what are the memory requirements, what are the stability, vulnerability characteristics, and other properties of those software artifacts. So if we drill down a little bit on the insights, on the knowledge that we want to gain from those, we have a certain categorization here. It's not meant to be complete, but it's meant to give a first idea. If we perform a static analysis of those components, we have rich metadata usually available, but also there the inconsistencies start. So sometimes we have, let's say, a software component where there's a clear information on who is the maintainer, where's the authoritative source code location, what versions of a certain platform does that deploy on. So if we have all of the information, we consider that a high quality artifact. But in practice, and we will show some graphs later, we see that this is not always the case. So we may not be able to deploy a software artifact, and then we look into the metadata and we don't see which version of a platform it requires. It may say it deploys on Kubernetes, but we may have a more recent Kubernetes and it simply does not deploy. And then we are looking for a person to contact, but we don't have an email address in there for a maintainer, for an engineer to contact. And so we consider that a low quality artifact. So the characteristics we are looking into are the completeness, consistency of metadata, the same for configuration files, which are also static files that we want to evaluate in most cases declaratively. Plus, sometimes, especially if we retrieve those artifacts from marketplaces, we also have dynamically generated data. So we see, for example, the popularity. Is an artifact popular? Is it downloaded a lot? Do people comment a lot? Do they downvote it? Are there critical remarks? So this kind of analysis can, of course, become another source of knowledge to understand the quality and the usefulness of an artifact from a static point of view. To go further, we can combine that with functional correctness. For that, we have to test the artifact, and that is hard to do in a generic way. It depends a little bit on the nature of the artifact. So if you have a Docker container, for example, it is almost impossible to test them generically. You can run all Docker containers, but whether or not they expect certain directories to be mapped or certain port numbers to be open, whether or not they even expose a service interface, that is very heterogeneous. It is not possible to predict that in advance without fully understanding the whole hierarchy of the layers in the Docker image and the instructions given in the Docker file. So there's currently no tooling available to be able to make any very generic statements, but we can still infer a certain amount of information. If we have a cloud function, for instance, it looks a little bit different. A cloud function is always a clear microservice, has a clear interface on what data it expects and what data it returns. Of course, we know that only from a syntactical perspective. We don't know from a semantic perspective what the function actually does or what the data means that it asks for or that it returns. Still, the generic testing there is a little bit easier. And once we have an application up and running, no matter if we do static or dynamic testing, we can also do the assessment of non-functional characteristics. We may be interested in the performance. So we may have two functionally equivalent artifacts that implement a database, for example, but one is faster to boot than the other. And especially in cloud environments, where we typically have a kettle principle of microservices, we want to quickly reboot a component in case it fails. So that may be a performance characteristic of importance to us. Security is similar. We have a number of Docker images available, all coming from different sources. Some may be coming from the official vendor, some may be third-party images. We may want to compare them based on the number of open security vulnerabilities or CVEs on them. And of course, if we go into those continuums, IoT hardware, we may also have certain questions about the compatibility. We may have a cloud application that requires GPU for deep learning, or TPU even, or FPGA for mining of cryptocurrency. So no matter what the application does, there may be a hardware dependency. And that is also something you typically do not find often expressed explicitly and consistently in the metadata, but it is something that a framework that we are working on should be able to extract, and so that you have the information, those insights available for comparison. Now, if we have all of the insights, what do we do with them? And that's a philosophical question we often ask that ourselves. We are generating lots of metadata and insights into those software artifacts and into entire applications. And why is that important? Who would use the data, right? So some scenarios are possible. One scenario is shown here is that you take an artifact from a public repository. Let's say you take a Docker image, container image from Docker Hub, and you notice that this one is flaky or has some issue in it, some quality issue, a bug, a security vulnerability. That means that when this artifact is instantiated, when the service interfaces are being enacted, as we have seen in the lifecycle model by Gkikopoulos, then those are not necessarily, but also potentially faulty, right? So there may be something wrong with them. They may not boot up correctly, or you send a request and after 3 requests, they start leaking memory. There may be an issue. And since they may be part of a composition, then this fault is transitive. It may affect other parts of your application, so that in the end, when the user goes to the front end of the application, even though the front end itself and the next immediate artifacts are not affected, there may be a reduction in user experience, and there may be an issue that is really affecting the daily use of the application. So it is very important that we try to be as strict as possible in only accepting software for our cloud application compositions that is of high quality. Let's make it a little bit more concrete. So far, my explanations have been maybe a bit abstract. Let's look at the Docker Compose syntax. That is something that is rarely used in production, but quite often in the development of containerized compositions. And that is a real example we have taken from our own labs with students. So students create Docker Compose files, and this echoes what developers are doing in daily practice. They often use copy and paste, and that is introducing a number of errors. We see two very typical errors here. First of all, we should have unique service names for each of the services, but we have duplicate names, and that is not a mistake that Docker will recognize itself. So Docker will happily start, but will let one of those services silently fail. That is something we should catch beforehand with static analysis. The second issue we see here is the port mapping. So we see that the port 80 is mapped to the MySQL port. Here it's done correctly because that's actually the MySQL container, but here it's done incorrectly. So in runtime, this will fail. Even if both services would start up, then the web server Nginx would redirect to the wrong port and would not be able to serve at that port because it may already be occupied by MySQL, or depending on the startup order, it may then block MySQL from taking this port successfully. There are a number of potential issues, even with relatively simple formats like Docker Compose. And this is even aggravating if we go to more complex formats like we have in, let's say, full Kubernetes deployments. We see another example here. So this is the example of Helm charts. We have Helm chart is typically an application package that may reference other charts as dependencies. So it can be recursively structured, and it consists of a number of templates which are rendered together with certain value files into manifests that can be deployed on Kubernetes. And those manifests, they are referencing images. Those images may be, as container images, be locally available on the system, or they may even just be on a remote hub like Docker Hub, and they may have to be pulled up on deployment. So we see that there are lots of connections in between, and if we start analyzing those artifacts, we have to trace down all of those dependency chains. We have to recurse, and we have to check that everything down there may affect in the end the quality of our entire application, which in this case is packaged as a Helm chart. So one study we already did, and that is something we come to later, is we have analyzed a number of Helm charts, basically all the Helm charts at that time available at the predecessor to Artifact Hub, which was called KubeApps Hub. And we see that there are a number of charts available, quite a few of them, that have a high number of duplicate values, which means that instead of putting them into a template and referencing them as variables from a values file, they are hard-coded in different places through the manifest files. And that is not a problem per se, but it is a maintenance problem. If, for example, a port number later changes, it needs to be adjusted in all of those files. Whereas if it was properly singled out as a variable, it would be sufficient to change it just in one place. So we see that there are some actual problems, but there are also potential problems that we can catch with static analysis. So after all of this background that has concerned us for many years, then about 2 years ago, we said we need a framework for that. We did not find a suitable framework. And as we are practical-oriented researchers, we set out to create this framework. And we called it the Microservice Artifact Observatory. It should have a dual use, so it should be useful for researchers, really, in the sense as an observatory that does regular long-term observation of public repositories of those microservice artifacts. And in that sense, it becomes a research infrastructure because it generates all of that data that data scientists can tap into and generate further insights. But it should also be, and that's of course one mission of our university, be directly useful to engineers, to developers and companies that create cloud applications. And so the same mechanisms for assessing software we want to make available in real time as CI/CD integrated tools, for example, so that they can be used to check an artifact that is just under development. A developer is creating a new version of an artifact and directly wants to assess it before it even goes out to the next stage of the development process. It's a community effort, so we are coordinating that, but there are already several universities from around the world linked to that effort. They take several roles. Some of them may not be that familiar with cloud technologies, but they have skills in data science, and they can mine and analyze and explore the data we generate. Others are more having an operational perspective. They run parts of the infrastructure without necessarily being interested in the data that is being generated or in the software artifacts that are being monitored. So this is, of course, also a call for anybody who is interested in participating. You can, of course, join that effort as well. Let's look at a concrete example of how MAO is making this happen. We, in the center, have a web of trust, an informal web of trust created by the operators of the infrastructure. MAO is a federated infrastructure. So instead of being a centralized entity saying this is the quality of a certain software artifact, we can run the monitoring, the assessment several times and simply compare. If none of the operators are in disagreement, then this is considered a ground truth. So if, let's say, 5 different institutions around the world all monitor a certain Docker image and all of them say this Docker image has security deficiencies, and this is recorded as ground truth, and certain decisions, informed decisions or even automated decisions, can be based on that. So if I'm an engineer, I can query this knowledge base and I understand this is a faulty container image, I should not use it. Sometimes it may be that there's disagreement between the different operators of the infrastructure, and that may be especially the case for the runtime tests. So the static tests, there may also be differences if, for example, different test and assessment methods are used or different tools are used. But especially for the runtime analysis, we may assess the same software artifact in different environments, and it may expose a different behavior. It may run very well in one platform and not so well in another platform, even though it still runs. And then we have a disagreement, and if we have disagreements, we are running a consensus algorithm to resolve the disagreement by voting majority opinions. And if the conflict cannot be resolved, we can even record both opinions. So then the knowledge base will say 3 out of 5 experts think that this is a faulty artifact, but 2 disagree, so it may still be valuable for you. What we do exactly with those disagreements, so this is something that in a later stage, data scientists come into the game, and they will be able to infer further knowledge. For us, it is important to record the knowledge in the first place, especially when we think about long-term monitoring of software artifacts, where any day that we lose historic knowledge of how certain software technologies evolved and the trends and certain changes in those artifacts. So we are quite engaged in capturing as much data as possible from an early stage on. There are a number of public cloud artifact repositories and microservice artifact repositories that we have been monitoring for many months now, and we do have the data, and I think we can use the data and make it available, let other researchers use it to gain more insights into how our software is working and what went wrong maybe in the past. How is MAO exactly structured? We see an architecture picture here. We separate between the MAO orchestrator that runs on each of those participating nodes in the federation and the containerized tools that may well be external tools. So starting with the orchestrator, that one takes a registration of tools. So we can plug in a number of assessment tools, and depending on that, the capabilities of MAO grow in assessing diverse artifacts. It orchestrates the execution of the tools. So, for example, it may have a schedule that Docker Hub is checked once per week, and your own private Docker registry in the company is checked once a day. And then the test tools and assessment tools are executed according to that plan. And all the test results, all the data generated by the tools is stored in an external volume. From there, it can be backed up or imported into further data analytics tools. MAO itself comes with a command line interface, MAO CTL, so that you can control all of the parameters I have just given. But it comes also with internal functionality. For example, measurements may go wrong. There may be a break in the network connection. There may be an out-of-memory error when running the tool. And all of that would lead to invalidated measurements. And that is something we have experienced a lot before we had that infrastructure, when we had just built some individual assessment tools. That happens a lot, and that leads to both gaps and also invalid data in the measured, recorded results. And for that reason, we have a number of detectors within the orchestrator. So, for example, if the values are very stable for a long time and then they suddenly change, that may not mean that the artifacts have really changed all at once, but that may mean an issue with the measurement. And so we can at least detect it. We cannot necessarily fix it autonomically, but we can at least inform the operator that something has gone wrong. To a certain degree, if, for example, the network is not available, the orchestrator will also repeat measurements automatically. And of course, it will perform the consensus voting. So in case reports come in from other nodes of the federation, and similarly, this orchestrator here, when it's part of the federation, will notify other nodes about its results. So then consensus voting is happening, and then the results are being stored. We are using etcd as a decentralized key value store for coordinating, which is a standard tool. So we have it available in most cloud environments. So that makes it fairly easy to integrate this MAO architecture into existing cloud environments. Let's have a look at a typical workflow. So we start with running the or registering, first of all of the nodes and the tools, the assessment tools. We sometimes call them crawlers as well. We come to that in a bit. As well as the data sets. And then in a second step, we collect all the data, we fetch all the data, and we store them accordingly. And then, of course, we have the raw data. So something we have been working on, especially this year, was making it possible to run data analytics on the collected data. So we have the ability to integrate MAO with data science tools and reproducibility systems that are increasingly used in research. Especially, we have already implemented an integration with Renku. So Renku is a tool from the Swiss Data Science Center that allows you to run scientific notebooks, Jupyter notebooks, R scripts, and so forth on data, and record knowledge graphs that show how data was produced based on which inputs, based on which tools, to make this more reproducible. And that is something we can leverage so that we can say we have the raw data available. That one we can only trust based on the number of nodes that have the same data. But everything based on that we can trust, because we have the full trace of how further data was derived from that. So if we, for example, take average values and the average metric is wrong because the formula is wrong, and then another researcher can come reproduce exactly the same calculation, but fix the formula and then achieve a fixed ground truth and can put it up for voting again. So we have a number of situations in which we can assess our artifact quality. Something we do a lot as researchers is in the batch way scanning the public registries and hubs, differing depending on how the access works. So some of them do not provide APIs. We have to do crawling. Some of them have APIs, but it's access restricted. And of course, we may have internal registries in larger development teams. So there we have typically no restrictions. And of course, we can also scan before the deployment in our local project folders if we are engineers. So that works as well. Very typical is the assessment in real time. If we want to migrate an image from one place to another, or an artifact in general, for example, from a developer, I'm pushing to an internal artifact repository to make my artifact available to other researchers. I could have a policy in between that only artifacts with a certain quality are allowed to pass. Similarly, if I try to pull a repository from a repository, which is public, into my development workspace, I may have a policy which is refusing that unless the image is somehow certified. So if we had such a case where we work with a bank and or an insurance company, and they are very conservative in that regard. They say that images need to be certified, otherwise they will not allow them to be propagated to the developers, because from that point on they may propagate into anywhere in their infrastructure. And of course we have other flows as well. Finally, we also should be able to perform an artifact analysis after deployment. So for example, everything may be all right with a Docker image, but then after deployment, we find out that a new security vulnerability gets known, and we want to check, does it affect our OpenShift cluster or Kubernetes cluster? Does it affect our deployment in AWS or the Google Cloud or IBM Cloud? And in order to know that, we have to run this analysis as well after deployment on a regular basis. So with all of those preliminaries, we come to the status. So how far are we with this attempt, and what can you already use for yourself? We have a number of artifact types that are supported. So we can scan Lambda functions and SAM files, so serverless application models. We can scan Helm charts and related artifacts, Kubernetes operators that are used to automate ops decisions in Kubernetes clusters, CNA bundles, and OAM files that are cloud application formats proposed by Microsoft, Docker Compose files, Docker files, of course, Docker containers. So we have a number of artifacts already implemented as part of our previous research and development. Decentralized applications, smart contracts here. All of that is rather prototypical, of course, because our main research here is building this infrastructure, but we want to also provide an immediate usefulness to the industry. Of course, in industry, most of the focus is on the Docker ecosystem, so Docker files, Docker images. Those are the strongest ones we see a need for, and when we interact with industry, they have a need for, they indicate a need for having quality checks on those artifacts. So we now have a number of tools available. We have those tools that are fully integrated into MAO, where you can just run MAO with the appropriate tools. We have a number of those pseudo tools. They are also integrated, but they are just used for research purposes or for testing, or as part of the workflow of the orchestrator itself. And then we have a number of older assessment tools that were predating MAO. You see that all of them have been published on Archive with an appropriate study. I think we have the links later, detailed links on the website. So all of those tools exist, and they are running each day or each night on our infrastructure, but they are not yet fully integrated into MAO. And we are working on integrating them, especially to benefit from the fault-tolerant and federated infrastructure that we have. So we get more high-quality measurement data, and so we can more easily assess and with more confidence assess the quality, security, and other characteristics of our software artifacts. To give you an impression, so some of those tools are not just programmatic tools, but they also come with a front end, so you can also use them web-based. This is something we do occasionally. Our students do that, and engineers in companies use that. we see the number of hits on those websites increasing. So we have the Docker Compose validator, where you can just upload a file or give a Git repository. It will check that. We are currently working on the same for Kubernetes manifests, and we have the same for Helm charts, for example, where we get all of the explanations on what should be fixed in case an error is detected or an issue is detected. But we also see, and that is very useful for us, we see that there's a public trend now of other tools being developed. So a lot of the companies in the cloud space, a lot of the cloud community, they have now also seen the need for more assessment tools. And so instead of just using our prototypical tools, you can also use those very mature tools that are certainly developing at a pace much faster than we could do as researchers. So our main aim then is integrating them into our infrastructure, because they come as standalone tools. They do not come with the federated fault-tolerant infrastructure. So the measurement results from them are not something that you can rely on, and are not something that is going into long-term archives as is done with our infrastructure. So here we see an example. The scan tool is a recent effort to get knowledge and insights into Kubernetes artifacts, where all of the objects within a Kubernetes manifest are checked and are described, and again, giving recommendations to developers. And here you see another tool, Declare tool, which is used to run security checks on Docker containers. And we built a tool around that already, which goes layer through layer through a Docker image. And so that if, for example, a layer you depend on, so for example, a base image has a security issue, there's no need to scan your image, because the probability is anyway very likely that almost guaranteed that you are affected by the same security vulnerability. So from that, we generated a lot of findings over the years. We do the trend analysis. We regularly run those checks, and we also dive a little bit deeper into finding potential issues. So for example, if you look at the lower right, you see serverless application models or serverless applications offered by AWS on their serverless application repository. We analyzed them based on the language, and we found, for example, that the number of total invocations we were able to perform and the number of successful invocations differed a little bit on the language, but also on the language version. You can see that, for example, in the Python support. So this is a slightly older image, but at that time, Python 2.7 was mainly supported. So the invocations were to a large degree successful, whereas the newer Python versions 3.6 and 3.7, so down here, it's a little bit cut in the legend, they were less successful. And so we are redoing those tests, and we gain knowledge into what is working and what is not working. At the moment, up until now, what we mostly did was writing custom scripts to get this knowledge. But as I said, we have now integration with Renku and other data analytics tools. So the idea is, of course, that you would have reproducible scientific notebooks to create this knowledge over time. So with that, I think I have given you a lot of theory, and you need to be able to digest that. And that's a lot easier if we go to the hands-on part. So now my colleague is going to run you through a couple of scenarios. You can really see how MAO is being set up, and how we are running a check on some artifacts, and how we also look at disagreements between nodes in a federation. Thank you for listening so far.
So thank you, Josef. And from my side, I would also like to thank the hosts for having us here. And my part is a hands-on demonstration of the current capabilities of MAO and its functionalities. And also, if time allows, a couple of real-world examples where we are using it in our current research. So let me share the screen and
Yes, screen is shared. You can just go to the application.
Okay, but I cannot share the entire screen then. Oh, I can just go to a different application and then it will switch. So can you see my slides now?
Yes.
Okay. Sorry about that. Because I will need to be switching windows a little bit to show the live demo. So the first example we are going to see is basically how a node is being bootstrapped. So how to initialize a node that is only now joining the cluster. So as Josef has already presented, there are a couple of backend components, and we are using a Docker Compose file to start those neatly and also manage the dependencies. But then for added flexibility, we also have the server component, which is a standalone program. So this is a snippet of the actual configuration file, the actual Docker Compose file here. And basically, in order for a node to join a cluster that is already running, it will need to receive some kind of credentials in order to enter in this file, to be able to connect to the other peers within the system in order to join the existing federation. So now I would like to switch to basically show you, hopefully you can see two terminal windows here.
Yes.
Okay, great. And one moment, okay. So basically now I can start up the backend components. Auto-completion has stopped working for some reason, but okay. Okay, somehow that file has been deleted. But anyway, what I actually wanted to show was essentially the Docker Compose part starts first, and then we start the server separately. But I can move on to the test system anyway for the other part where the infrastructure already works. To move to the second part of the demo. So the next part is basically how the registry is interacted with by users. So the registry can be used to register a tool that a certain user has created and would like to contribute to share with a cluster, which will allow other members to invoke it automatically, provided that they have the MAO orchestrator system running on their infrastructure. So here we can see basically a snippet of the help text for the CLI, which basically shows us the arguments that can be added in order to register a tool. Of these, the image and data repo are the most important because those are actually used by the orchestrator to invoke the tool using Docker and also to download the sample dataset that will be used as a starting point, but that can also be overridden. And in addition, there is also the dataset entries, which basically include have a directory structure of basically the parent dataset and then the individual node datasets with the links for how the orchestrator can retrieve them. So to show a demo of this, we go to the system. Here I will show you the server in foreground mode. And then we will also use the CLI to add the tools. So for example, this is an example of how to add a specific tool to the registry. So here we can see that I am naming this tool Artifact because it is meant to monitor Artifact Hub. And I have a sort of short name for myself as the author name. Then I tell it, OK, you can use this public image to invoke the tool, and then also where to download the sample dataset that I already have. Here on the server side, you can also see the notifications that are starting. This is basically a system for already run experiments and tools that notifies the user that some kind of data spike has been detected at some point. And of course, the idea is that not in a test system, but in a real system, these are not just logged, but also can be used to alert users that something abnormal is happening. And so, of course, the registry can also be used to search for tools that are already registered. So, for example, by doing tool get, we can see a high-level overview of all of the tools that are here. Of course, because this is my test system, a lot of these tools are just testing.
Now we unfortunately lost him, so let's be patient. Let's wait a minute. I think he will just join back now. So in the meantime, let me already give you the opportunity to ask questions. As long as the demo presentation is being done, I can monitor the questions section of this session, and some of the questions I may be able to answer directly in text form, and some others I may already think of a potential answer that I can give then after the presentation. So do not hesitate to ask already now if you have any question about what we are doing or how it may be useful to you, or what is your context. Are you maybe developing software in a company? You need certain quality tools that we have not covered yet, or you're looking for something specific, then that is, of course, a very important input to us.
So to the audience, as Dr. Spillner said, if there are any questions, we're happy to have you on stage. Okay.
Yeah, folks can also type in questions or into the window, or make suggestions, questions. Normally, we would have this very interactive in a typical face-to-face setting. This is, of course, now is the time you have to ask questions, so please go ahead.
So maybe Dr. Spillner, I'll ask you a question. So at least in this part of the world, India and APAC, we read that only about 10% of applications have been modernized, and that the remaining 80 to 90% of the applications is still legacy VM based backend software, especially, and only those applications that are comfortable off premise are the ones that are target for modernization. And when I say modernization, it's not merely transforming or rewriting monolithic software into microservices, but it is also the concomitant transformations such as storage transformation. So applications that leverage, from a performance perspective, the applications that were used to say high IOPS storage arrays now leverage software-defined storage, right, that is abstracted by things like OpenStack Cinder and Kubernetes and so on and so forth. So the pace is slow because of the difficulty and the investment needed to attack the backend and rewrite all of this. One of our earlier tutorial speakers was talking about from Google, his experience around working with a customer that had a huge base of COBOL code and how difficult it was from a modernization perspective. So in your part of the world and your circles and the research in the university, what do you see?
Mm-hmm. So certainly we have a wide spectrum as well, as we are a banking country. You cannot imagine what legacy code is available, even mainframes, of course, in our banking world. But we do certainly have that other end of the spectrum that is now very open to clouds. Especially now we have been one of the last region in this part of the world to be a hub for the major cloud providers, also all the global cloud providers, the hyperscalers. They are just now entering Switzerland. So I think we got Google 2 years ago. We will get AWS in 2022 only. But we do have a number of smaller cloud providers, quite healthy ecosystem around here. And some of them have been, because they came later than the traditional large cloud providers, they have been entering the market without the historic, let's say, baggage of older cloud infrastructure. So we have providers that from the very beginning offered only containerized infrastructure, for example. And so, of course, there was pressure on the companies that wanted to be hosted around here. And for certain needs, for certain industries, it has to be hosted in Switzerland. So they had essentially, they were forced by the regulations to use a domestic cloud provider, and they had to go with those newer technologies. So the pressure was very high on them to modernize their software stack. A lot of them came from the maybe Java enterprise world, or from those kinds of systems, where it was, of course, facilitated to repackage their software so that it runs in the cloud, but exactly with the issues that we described. So some of the artifacts, some of the applications, they are somehow running, but they are not maybe running very well. They are not using the cloud to its full potential. They may have certain drawbacks from a financial perspective. So you know that cloud computing is a very financially attractive paradigm if you use it correctly, but it can also be the opposite. It can be very, very costly if you do not use the right facilities and service models. And so for some of them, that is also increasingly an issue. And now they are looking into not just, after they have taken the first step of bringing their applications into the cloud, they are increasingly concerned of getting the quality right and following best practices, making sure they do not violate certain conventions. Something that we have had in traditional programming for a long, long time. We have all of those linters and tools, test coverage tools. And we are just now starting to see that on a cloud level, which is similar concepts, but on a completely different level.
Okay. And you mentioned banking and Switzerland. So recently, we were trying to sell cloud to a bank in Switzerland, and the CTO commented that there was a lot of backend software running on the mainframe, and the attempt was to get the bank adopt multi-clouds and become more cloud native. So the comment was, for me, AWS and mainframes are both similar because both are non-standard and not open. So why would I have already a team and I have invested in the mainframe. So why would I go to cloud? Because there is no, it's not standard based, it is proprietary API based. So I don't see a difference. So what would you say to that CTO?
Well, I don't know what I would say because I'm not trying to sell. But from an observer perspective, from my academic view, that works very close with industry, I would say there are, of course, successful models where the cloud provider is just chosen to be a heavy infrastructure lifter, and everything on top is self-managed. So instead of using all of the facilities by the cloud provider, just use the basic ones, VM hosting, for example, or container hosting as the baseline. And then anything on top of that you manage yourself so that you can more easily migrate to other cloud providers. So the more, of course, you use the facilities of a cloud provider, then the more you get locked in. And of course, there's a certain tendency or a certain magnetism that if you are a large institution like a bank, then you get certain customer representatives that look with you at the application and that will try to upsell you into more offerings by the cloud provider. And so they are finding a fine line and not always following every advice, but looking what is really the best for me is something I would recommend. And they are, of course, as a university, we are well positioned because we can give independent advice. We have many years of experience. We have looked at many industry projects, and we are certainly neutral. I mean, Switzerland is a neutral country, but within Switzerland, I would say the universities are very neutral instances that can be referred to as experts to look into a certain constellation and give at least an advice which direction would be preferred, which direction does not lead to nowhere.
Sure. I think we have Panagiotis back. I can see him. Shashi, can you bring Panagiotis back on stage?
Yeah, sure.
Thank you, Dr. Spillner.
You're welcome.
No, Dr. Spillner, if you have a contact number of him, could you call him and ask him to refresh his browser? Sri Krishnan, he is in attendance, but we are not able to bring him on stage. Possibly it is due to some issue from his browser. He just need to refresh his browser.
So Panagiotis, if you can hear us, could you type something in the chat window?
So I already tried to contact him, but it did not work out. So I also see him in the attendees list, but I'm not sure if it was the kind of ghosted.
Yeah. Any other questions from the audience for Dr. Spillner?
So he's trying to rejoin. So as he was giving the demo in full screen, initially he did not notice he was dropped. So he should be back in half a minute latest.
Okay. Yeah, he's back. Welcome back.
Okay, so how far behind was I? What was I talking about when you lost me? Because I only received it when I received a message from Josef that I had dropped out.
So I think you have been in the second demo. Just about to install about to register the tool, the Artifact Hub tool.
Oh, okay. So that was a long time ago then. Okay. Okay. So hopefully you can now see the terminal screens again.
Yes.
Okay. Right. So for the registry demo, as I said, we can register tools and datasets. So in this particular case, of course, it is already registered, but I can just overwrite it. So I can just add a tool here. So this is the Artifact Hub tool, and I'm listing myself as the author, and then I'm telling the orchestrator that it should use this image to invoke it, and then it should also get the reference dataset from here. And basically now I can register it. And of course, I can also use this CLI tool to get it to retrieve it. So I can get it by name, and it will give me back this exact entry. And we can also do the same thing for datasets. So I can add now a reference dataset here, which will register this dataset to nodes that want to use it. And then, of course, I can retrieve it the same way, essentially. So, and then it returns me back the link to tell me that this is the dataset that has been registered there. Okay, so I will just go back to the slides, but I will run everything a bit in fast forward, so apologies for that. So for running the tools, we can give the orchestrator the run command, and that also includes the name of the tool and also the dataset we would like to use that overwrites the reference dataset in this case. But we can also schedule the tools to run periodically, in which case we can set it to run, for example, daily or weekly, but we can also use cron-tap syntax for this periodic invocation. So in this particular example, we will invoke exactly this tool that we just registered. And it will now run it. And at the same time, it will also show us some scheduler information. So we see, for example, that this is the image that we are invoking, and this is the name of the tool that we have registered. This is where, according to the configuration of this test setup, the tool will save the data, and these are some optional parameters that we did not use, like integration with some data platforms and optional commands we can give to the scheduler to basically pass through to the Docker API. So the tool would now execute. Now, this tool execution takes about 90 seconds normally, so unfortunately, I might have to stop it in the interest of time. Yes, so I will stop and restart the scheduler, because then we may not have time for the second part. So then we can also use the schedule command to schedule the tool to run periodically, so daily or weekly or something else using cron syntax. And okay, so we registered our tools and our data sets. We have run our tools. Other nodes have also used our tools, and they have gotten their own data back. And basically, then now is the time to reconcile conflicts and also missing data between the nodes. So for this example, I have set up 3 reference data sets, which pretend to be from different nodes. And this includes data snapshots from 2 real data sets that we have. One is metadata from Docker Hub, and one is metadata from the AWS serverless application repository. And there's also a custom metadata file included that is used by the consensus module to understand how to read those data files. So this is a sample of what the Docker Hub file looks like. So we have about 500 entries by date, and we can see here how a certain subset of Docker Hub is evolving over time, and that includes CPU architecture support and also OS support. And also, this is what the SAR file is. And of course, here I have also inserted 2 malicious values, which we aim to get caught by the consensus system. And here is a sample of what the metadata file looks like. And for example, it includes the file prefix that it should look for in order to identify the files, the index column of the files, and also a separation between numeric values and non-numeric values, because these are handled differently by the consensus algorithm. So with that in mind, we can now go and invoke this demo. So first of all, I'll have to delete the fake data we just tried generating it, because it might be corrupt, because we had to stop it. So okay, and then we can invoke the consensus module. And basically what it does now is it will clone all 3 of these data sets that I have already registered, and it will run exactly this consensus algorithm and produce the results. So the results include an aggregated file that includes all of the statistics, so minimum values, maximum values, and average values. The ground truth dataset that has the same format as the original dataset, and also a report on outliers. So for that, we will go back to the slides. So yes, as I said, we have the ground truth dataset, which follows the original structure. We have the aggregation statistics, and we also have a JSON file that informs us of outliers that have been discovered. So here, because we have a very small sample, the outliers could not be efficiently detected. I have discovered through experimentation that we need at least 10 nodes participating for this. Otherwise, the values are all taken into consideration and are averaged together, which can create an anomaly in the numbers. But of course, for the actual consensus voting, it is much simpler, because we are just voting on values. So you can see here that one node tried to pretend that the function called Alexa Skills Kit Color Expert was written in ancient Greek, but the other 2 nodes actually voted for JavaScript. So this was the actual value that was picked in the end. So this is the end of the practical demo. I hope that would have some time to show 2 real-life data sets, but I think in the interest of time, I would have to skip that and go back to Josef for some closing remarks before we go to questions.
So since we already had some questions, I would say we can maybe quickly show at least one of the data sets, so that we can convey a little bit more how they look like and how they would be integrated.
Yeah, that's a very good idea.
Okay, so I will go back to sharing then. And let me just stop the scheduler for more screen space. Okay, and now we can show the Docker Hub dataset. So this is an export I made from one of the nodes. If I just list the files, you will see that it has been running every day since, I think, November 19th, 2019. And it basically produces a raw output JSON file every day. And it also produces some example graphs. So I can open one of
Again, we lost Joseph.
It looks, unfortunately, he dropped again. I'm not sure what is up with the system. Then I think, oh, here's back.
Okay,
Yeah,
so
he's on
yes,
straight again.
this time I found it easier. Okay, so let me go back to sharing the dataset.
Could you also share your screen? Yeah.
Yes. So again, this is an example of a directory where I have exported locally an entire more than 200 days of data monitoring. So basically, the raw data that is being collected from Docker Hub itself is these output date .json files, which is exactly.
So it looks like we will not succeed with this demo. Then I think what I will do is I will share the final screen, and there you find the resources and the links, and you can, of course, explore by yourself. If Sri Krishna, if this is what you recommend as well, Dr. Gopal.
Yeah, that's fine.
Yeah, okay. So let me just share my entire screen and then the presentation. So here what you see is the website for our overall community effort, this GitHub.io website. You also find the link to our code repository. From there, you can, of course, download the MAO system yourself, run it for yourself. But on the observatory page, you also find links to the data sets so that you can also explore the data for yourself. You also find some videos listed there. And of course, on the shared folder that I've just written in the chat during the presentation, you find the transcript where you can run a number of the commands we have shown in the demo by yourself. So if you're interested to scan certain artifacts, we show you how to do that with our own tools, but also with existing tools that we know from other sources. So assessment tools, check tools, as long as they cover those newer cloud technologies. So with that, we conclude our presentation. So sorry for the technical difficulties. And of course, if anybody wants to follow up bilaterally after the presentation because you did not catch something, then we are happy to do that as well. Since we had some unanticipated technical problems, we will check later what was the course. And with that, I think I'm still available. Maybe my colleague will also check back in a minute for answering questions.
Sure, thanks, Professor Spillner, outstanding session, very scholarly. And like we said before, from the audience, if there are any questions, we'll have you on stage. Okay, I think we can then conclude this session, perhaps. And like you offered, you are on email, and people have questions, they can approach you as well. So thanks for that offer.
Thank you very much for hosting us. We hope you enjoyed it. I saw that the participation count was even increasing during the presentation. That's a good sign.
Yes.
Overall, I think it was a very nice conference, and I think what follows now is the closing session, so I don't want to be too much in the way of that. And with that, I think we can hand over to the hosts to the next session.
Thanks, Panagiotis, to you as well.
Thank you.
Thank you all. Sri Krishnan, I will end the session now. We move on
Yes.
to the award section.
Yes, yes.